Alright, so today I'm gonna be explaining another important article with the title Liftpool, Lifting-Based Graph Pooling for Hierarchical Graph Representation Learning. This NURIPS paper in 2020. Graph pooling has been increasingly considered for graph neural networks to facilitate hierarchical graph representation learning. Existing graph pooling methods commonly consist of two stages: selecting the top-ranked nodes and removing the rest nodes to construct a coarsened graph representation. However, local structural information of the removed nodes would be inevitably dropped in these methods due to inherent coupling of nodes and their features. So location and signal are coupled. This is referred to as, for example, positional encoding. This is referred to the original attributes. So we propose an enhanced three-stage method via lifting, named Liftpool, to improve it. So it introduces an additional stage of graph lifting before graph coarsening to preserve the local information of the removed nodes and decouple the processes of node removing and feature selection, feature reduction. Specifically, for each node to be removed, its local information is obtained by subtracting the global information aggregated from its neighboring preserved nodes. Subsequently, this local information is aligned and propagated to the preserved nodes to alleviate information loss in graph coarsening. So they show that it is localized and permutation invariant. And the proposed graph lifting structure is general to be integrated with existing downsampling based graph pooling methods. You see the illustrative diagram of the proposed lift pool. The upper figure shows previous two-stage pooling methods consisting of node selection and graph coarsening. An additional graph lifting stage, which is the bottom figure, and you see that nodes with their associated features are first split into two subsets. For nodes to be removed, prediction operation is then adopted to compute their local information by subtracting global information that can be predicted from the preserved nodes. And finally, the local information of the removed nodes is aligned and propagated into preserved nodes via update operation. So here we remove global information and then we propagate the local information. So different from classical spectral-based transforms, lifting structure is characterized by the entire spatial implementation, providing us with an easy control of locality in a sparse signal subset in spatial domain. So an entire lifting structure is composed of two processes, a forward lifting and a backward lifting, which performs forward and inverse transform. The forward lifting process consists of three main operations: signal splitting, prediction, and update. So we describe the lifting structure over a discrete signal residing on 1D grids, and the signal x of n is firstly split into two disjoint subsets, an odd subset and an even subset. You know, these things in graph signal processing are becoming more and more important. Note that we take an equal splitting here, for example, and in fact any non-overlapping partition of x is also possible. which provides us with the flexibility to partition the signal into two arbitrary disjoint subsets. Then a prediction operation is adopted to obtain the high-frequency signal representation by subtracting the local representation prediction from even signal. For example, in elementary mathematics, you write the Taylor series of a function in terms of sign, and then we have a set of low frequency, and when the coefficient the frequency becomes higher, we have high frequency terms, and the split is up to you. For example, you get the first three terms as low frequency, the highest terms of Fourier series as higher important variables. So with the same analogy, they have done this for graphs. So now an update operation is adopted to process these high frequency signals and propagate them to x sub e with an update operator, which can be formulated as this. Through lifting, x is compressed on the even subset, obtaining coarser approximation. Essentially, the lifting process is a decorrelation between x sub e and x sub o, where the redundant global information that can be predicted with x sub e is removed, while the local information that is distinct on x sub o is distilled and propagated to x sub e to generate a more accurate approximation. So you see the forward process and the backward process as the equation was. So we do splitting, then prediction, then update. So for node selection, the structure-based criteria are commonly utilized to select the most informative nodes. For graph coarsening is obtained using this, that there is only one non-zero value for each row, and the coarsened graph features are updated like this. And then the idea is Liftpool. To solve the inherent limitation of two-stage pooling, Liftpool introduces an additional graph lifting stage to propagate local structural information. Thus, graph coarsening would drop less structural information and yield more effective hierarchical graph representation. In the proposed three-stage strategy, the additional stage of graph lifting is inserted between the stages of node selection and graph coarsening. So the graph feature maps are transformed to generate lifted graph feature maps. This is important, the permutation invariant node selection. We adopt permutation invariant attention-based methods, which is also done in SAGPOO. I've explained this in a different video. The self-attention mechanism is leveraged to jointly consider graph topology and node features in node selection. An additional graph convolutional network layer is developed to yield the attention score to determine the importance of each node. Then for graph lifting, the local structure is transformed to this for graph coarsening. So we formulate this stage of graph lifting like this, and these are the parameters that should be learned. In hierarchical graph representation learning, spatially localized and permutation invariant operations are usually preferred. The extra computational complexity and parameters should also be reasonable for fast inference and suppressing overfitting. Therefore, GCN-like graph lifting operations are developed to satisfy these requirements. And then graph coarsening. Graph lifting compensates the preserved V with the transformed local structure. Finally, we calculate the reduced graph with the coarsening matrix D. You see the overall structure. We have graph convolution, then lift pool. Graph convolution, lift pool. This continues until we have a readout, because we want to do a classifier, so we need a single vector. They did it for these typical data sets for graph classification, especially D3. You see that it is better than Liftpool. It's better than Liftpool. They've done it for 20 random seeds, so that's why they can also capture the variance of that. So the variance is reduced when you go from Liftpool to Liftpool. Also, the accuracy is improved, both of them, both the mean and the variance. And you see it even for different data sets. It's an improvement. If you compare it to Liftpool, this Liftpool is much better. And they did it for GCN and graph attention. They compared with graph stage.